But the MHC2 cells, those are the ones that basically the antigens are being presented after digestion, and that's going to be presented to the CD4 helper cells, which are going to in turn stimulate the B cells to produce antibodies. Jean was telling me this is the questions that she's noticed are in almost every serology review book, and several students have mentioned them on boards. So I want to make sure that I was clear enough, and I don't feel I was clear enough in lecture, that when we get to the end of that and it's presenting those antigens, that in the viral or in the infected or tumor cells, those are going to go to the CD8 cells, and in the MHC2 class, where we're presenting just the bacterial or foreign body antigens, those are going to the CD4 helper class. And this becomes very important when we start looking at HIV and AIDS patients, because these cells right here, this mechanism is working just fine. This is the one that is screwed up in our AIDS patients. I hope she didn't know this. Shh. But I don't feel like I covered that adequately.
Is that CD number 8? Is the AIDS patients?
Yeah. That's why we monitor their CD4, CD8 ratio, and we'll discuss that when we actually talk about HIV. All right, so we've already talked about, well, first of all, do you have any specific questions? I'm not going over the test because we have somebody still to take it, but if you have any specific questions on the test that you want me to address, something that's niggling at your mind.
Humoral immunity?
What?
Humoral immunity? What that?
Humoral immunity?
Yeah.
That is B cells producing antibodies. Yeah, you've got cellular immunity, that's going to be your cytotoxic cells, cell-mediated T cell, and humoral immunity is regulated by the B cells that produce antibodies. And I found out the answer to your question about the light chains. Approximately 3/4 of your antibodies will have lambda chains, and about 1/4 will have kappa chains. So each individual antibody will have either kappa or lambda, but they won't have both. So. All right, so we talked about phagocytosis and primary response. And a lot of you, when you were doing your essay questions, talked about the macrophages with phagocytosis. Please don't forget that the neutrophils are also very active in our phagocytic process. Okay? And in fact, as their granules contain peroxidase-based chemicals which fight off the bacteria. We talked about making antibodies and forming antibody-antigen complexes. The last kind of big piece of the puzzle is complement. Complement is a series of proteins that acts as a cascade, much like the complement or the co-ed cascade that you learned. Complement is also a cascade of proteins. You don't have to learn all 30 proteins. We've only got a handful of them. It says synthesized in the liver, which is kind of redundant because where are all proteins synthesized? In the liver. They do play a major role in the inflammatory response. These are kind of the end game. Okay. When we discussed opsonization, that little term, this is where that comes into play. They basically are an enzyme to digest bacteria and to lyse red cells. The lysing red cells is not something we want, but it does happen. It's important to remember that all of these components are heat labile. Okay? If they get too warm, they disintegrate. So if you're doing any kind of testing to measure the levels of these things, you're going to need to keep them cold. You cannot let these get too hot. And in a lot of our serology testing, not so much the newer methods, but a lot of the older testing, complement would interfere. So the first step in many of the initial serology tests was to put the specimen at 56 degrees for anywhere from 5 to 30 minutes to make sure that you destroyed all of complement, so that you were making sure that when you were measuring the activity of it, you were not measuring complement that was just being spontaneous. I found a better picture online, and we're going to go over it using that picture, just because I like that picture better. Okay. There are two pathways. There's the classical pathway and the alternative pathway. We're going to start with the classic. The classic is started with a C1. This is activated by the presence of the antigen-antibody complex. Now, we talked about antigens, we talked about antibodies. I guess I should have been more specific. The whole purpose of forming antibodies is to hook onto that antigen and form this antigen-antibody complex. It does a couple of things. It will agglutinate as well. It will pull these things all together, kind of hold them in one spot. And we'll talk a lot more about agglutination as a methodology later. But it will hold these things all together. This FC portion of our antibody, once this is activated into a complex, will activate C1, specifically C1Q. The C1 molecule is QRNS. I don't know why they started with Q. I'm guessing there's a CA through but that's probably part of those 30 ones. But the one that we really look at most is the C1Q. And what C1 does, the Q is then split to R and S, and those will break down 2 and 4. Okay, so 1 does 2 and 4. The 2 and 4, the A portion of 2 and the B portion of 4 are going to form C2A, C4B complex. The other pieces are going to sort of float off, and we'll talk about what they do in just a minute. The primary thing here is whether we activate from the classic pathway or whether we activate from the alternative pathway. Our key player here is C3. So in our classical pathway, C4B, C2A come together and activate C3. C3A floats off into space. C3B then activates C5. I won't ask you that. You not gonna have to draw this. Okay. I won't ask that. I don't know, future classes, maybe. I'll let you guys all decide. In the alternative pathway, we have factors B, D, and P, which is properdin, and some other little beasties here. We also have C3, which just will spontaneously sort of disintegrate. Obviously, if we have a cascading system, what do we have to make sure doesn't happen?
A step's not missed.
Pardon?
A step doesn't get missed.
More importantly, we have to make sure it doesn't run amok. Alright, so just like you have natural anticoagulants that help us regulate the coag cascade so that you don't just turn into one big large clot the minute you're born, we also have a lot of inhibitory things which regulate this pathway, especially the alternate pathway where C3 pretty much just splits on its own. Healthy cells have inhibitors on their surfaces which keep this C3 from sort of running amok, to make sure that it is only active when we have actual pathogenic organisms or pathogenic things present. What happens here, C5 gets cleaved into A and B. Then 5, 6, 7, 8, and 9 basically make a channel into the microbe. And through that channel, we can funnel water. How? Simple diffusion. The diffusion gradient, there is going to be much higher concentration of salts and things inside the cell than outside. So basically, this pokes a hole in the cell, the water gets in there and blows up the cell. Okay? So this forms kind of a water channel, a way for the diffusion of water to go into the cell. That's what our cell membranes are for, to keep that from happening. But if we poke holes in it, the water can get in and blow it up. And that's how this works. C3b also coats the outside of the membrane. That's our opsonization. And that makes it more attractive to phagocytic cells. These little ones I told you to just kind of, hang out on the other places, what they do, these are chemotaxins. And a chemotaxin is a chemical attractant, okay? It's kind of a little pheromone for phagocytic cells. It says, come over here, doesn't this smell good? Don't you want to come see what I got cooking over here? It's yummy. It also attaches to surface receptors on basophils and mast cells. And what this does is forces them to those dark blue granules that are in our basophils, and mast cells are simply just basophils that have made it into the tissue. Okay, sort of like monocytes and macrophages, that's basophils and mast cells. So basically it makes these granules release the histamines. What the histamines do is they dilate the arterioles, they make it easier for the complement components, for the white cells, for the phagocytic cells, to come into the area. This is why there's swelling at the site of an infection or something, because basically it increases blood flow to that area by releasing these histamines, and that makes everything kind of come into that area, makes the fluid increase in that area, and everything else to kind of cause the swelling. So in a nutshell, this is the complement cascade. There are dozens of pictures online. If you find one you like better, let me know. This is the one so far that I've liked the best. I had one last year that I thought was good. I think this one's better. I don't know, maybe just because it's got cute little shapes instead of just the nut. But the biggest things to remember, C1, 2, and 4 are the classical pathway. That I will ask you to remember. You need to know which ones we find in the classic pathway. That's 1, 2, and 4. Okay. C3 is activated by either of the pathways, and to some extent, it actually just sort of, pops on its own. C3 then affects C5, and that connects with 6, 7, 8, and 9 to make a channel through to poke holes into the membrane of the invading or the sick cell. It's important to note here, now while this is an IgG molecule, IgM will also bind complement. So both IgG and IgM will bind complement, yes.
What are these? Are they proteins?
They're just proteins. They just float around in your system. Very creatively named complement protein 1, complement protein 2. This last batch here are known as the MAC, which is the membrane attack complex. 5, 6, 7, 8, 9. That sounds like a good test question.
So what I'm sorry. C5 is the last step before it goes into the cells. That's what is building up the cell to make it burst.
No, C5 gets activated, again, it's C5, they actually, C2A, C4B is known as C3 convertase. A lot of these partial proteins that are here are enzymatic. They're proteolytic. They will slice a protein into pieces. And what happens to C5 is C3b is proteolytic, and it slices C5, which releases another enzyme which slices 6, 7, 8, and 9 and lets them bind together.
So C6, 7, 8, 9 are what's filling up the cell.
6, 7, 8, well, they don't fill the cell. They create a hole.
They're the ones that are lysing the cell in order to
Okay,
for the water
here's your cell membrane, okay? You've got complement, and remember, this will happen all over it. Okay, basically, the end product is this. It's a channel that opens a hole. Okay, this is your 5, 6, 7, 8, 9. This is your MAC. Okay, and what happens, I have water out here. I have less water in here. Diffusion says if there's more out here than in here,
move it.
the salt and stuff is going to come out, the water's going to go in. As the water goes through this now open hole, this open channel in the membrane, what happens is it fills this cell, and as the cell fills with water, it overextends how much the membrane can stretch, and it makes it pop. Okay, so this literally is physically pokes holes in the membrane of the invading cell.
What did you Google to get that image?
Complement cascade.
Complement testing?
Yeah, complement cascade images.
And that's not necessarily a cell. That could be a molecule. It could be, or am I?
No, it has to be a cell. It can be a bacteria, it can be a tumor cell, it can be a red cell, it can be a fungal cell, it can be a parasite, but it has to be a cell.
Okay, so essentially it's causing a demon and a parasite or something like that?
It's causing a hole. It's physically going and poking holes in the membrane,
Which is going to cause the cells to swell.
which is going to make it swell and blow up. Yeah. This is not a representation, or no, it physically pokes a hole in it. It's not just an analogy. It actually goes in, goes through the membrane, and goes like this.
What is attracting it to that particular cell, whichever cell it attacks?
The immune complex.
Okay.
So the antigens on the exterior of the cell are antibodies hook on. This immune complex activates C1.
But all of this is extracellular, so what is causing it to go towards that particular cell?
The antibodies are attracted to the antigens because
But that's the complex, that's not the C5, 6, 7, 8, 9.
right. This is floating around in your bloodstream all the time.
Yes.
Okay. We talked about the major histocompatibility complex, right? Your body comes in, phagocytes come and eat these microbes, vomit up the antigens, which makes your body make antibodies.
Yes.
The antibodies then hook onto others of that microbe that are floating around in your system. Okay? This complex that they form then attracts the protein C1, which is just floating freely in your body. Because this happened, it activates the C1. The C1 then finishes the cascade and pokes holes in that.
Okay, so the complex isn't just attracting the C1, it's attracting all of the complex, or the...
It's not
proteins.
attracting anything. They're just, these molecules are surrounding this at all times. They're just in your plasma. And it's just grabbing one that's floating by and says, hey, come here, you need to get a hole in this guy. It's an invader.
So that's why the portion of the antibodies on the end is the FC and left open for the complement system to come in and help.
Correct. Yeah, this can also bind, there's a lot of things the FC portion can do. In this particular case, yes, it's attacking, or it's attaching to the C1 molecule and causing that, it's causing the C1 molecule to reconfigure itself and cleave C2 and C4. Okay. This FC end can also be on our B cells and T cells, so that the AB end is floating around and it will attach when it finds it. So antibodies do a whole bunch of different things. But in this particular case, these antigens have been presented to the helper cells, which make the B cells form the antibodies, which then start floating around. And as they find this invading organism, whatever it is, they attach to it. When this complex is formed, this FC end is kind of dangling out there, and it grabs any C1 molecule that happens to be floating past and says, hey, come here, you need to take care of this. Well, there's millions of these C1 molecules floating there at all times. So every time an antigen-antibody complex is formed, it automatically initiates this C1. And there are inhibitory mechanisms to keep this from running amok and bursting things it shouldn't. But this antigen-antibody complex starts this whole complement cascade. Excuse me. And then as the microbes are destroyed, there's no more microbes running around for this antibody to hook to, and that stops the cascade.
They should have made the microbes the same color.
Huh?
They should have made them both the same. You know what I mean?
Yeah, they should have,
That would have made more sense.
probably. One of these days I'll learn to draw.
Just saying.
Yeah, I don't know why they chose the color. This is better than some of the other ones. If you find a better one, hey, please, shoot me the link. I haven't found one that's perfect. I haven't found one I really like yet. But this one wasn't too bad. So we've got three basic things that come out of our pathways here. We've got two pathways, both of which hit the C3. Okay, so C3 is this is the most important piece as far as activity is concerned. These extra pieces go over and attach to mast cells to increase circulation and to produce chemotaxins, which call in the macrophages, okay, which sort of entice them to come over into the area and gobble up more of these things, which then present the antigens to the antibodies, et cetera, okay. C3b hooks onto the exterior of the microbes, making them tastier for our macrophages. It also activates C5, which then hooks to 6, 7, 8, and 9 in our membrane attack complex, which physically pokes a hole in the membrane, allowing the water to come into the cell and blow it up. That is the complement cascade in a nutshell. There are a lot of other factors that go into here, and like I said, there are inhibitory pathways, as in any cascading protein pathway that's in your body, the kinin pathway, the coag pathway, complement pathway. There are always inhibitory mechanisms to keep them from running amok. To me, the coag cascade was always proof for the existence of God, because how you stopped it from just turning into one big clot the minute you were born, just the whole regulatory mechanism is amazing. Any questions here? We don't know enough to ask questions.
Is there any way you could print us out a picture of that by chance?
I don't have a color printer, but I can.
I don't mind it black and white.
I mean, I can copy the link.
That's fine.
Do that.
Me? I have round magnetic pictures, like I can't even remember
I would refuse to get involved.
I always
if you go to the course content here. Let's see if it'll let me do this. Okay, does anybody see the hyperlink?
Isn't it next to the text?
The HTML? Or no? What does that say?
Oh,
No.
no, that's code view, we don't want that. Believe me, that's confusing. Yeah, here's the hyperlink one. Here's another one I had last week, so I'll work on making this better, but for now, at least it's there, okay? For now, at least it's there. So you will need to make sure that you can identify, you need to remember that antigen-antibody complexes, only those with IgG and IgM. IgA, IgE, and IgD do not bind complement. Only IgG and IgM bind complement. So once your antibody antigen complex is made, the recognition unit is C1, which is C1q, C1r, and C1s. The activation unit is 4, 2, and 3. 4 and 2 are cleaved. The pieces of that come together to make a compound protein, which then cleaves 3. 3 cleaves, the activated 3 cleaves 5, and 5, 6, 7, 8, and 9 are the ones that poke the hole. You need to know that in the recognition unit is C1, in the activation units 2, 3, and 4, and in the membrane attack complex is 5, 6, 7, 8, 9. Isn't it nice that they're actually in order? Okay, so all you have to remember, there's 1 here, there's 3 here, and there's the rest of the 4 here. And then you just have to remember which ones are there. All right. These anaphylatoxins, okay, this is a word I didn't use and I should have when we were looking at it. Remember I told you the pieces that bind to the mast cells and the basophils and release histamine, those are anaphylatoxins. That's where we get anaphylaxis from, for an anaphylactic reaction. Okay. So anaphylatoxins, they bind to the mast cells, the basophils, and increase vascular permeability. The chemotaxins, we talk about those. They encourage the phagocytic cells, and in this case, these chemotaxins, I guess the neutrophils have a better sense of smell. Okay, but the chemotaxins are particularly attracting in the neutrophils. And the opsonins are the things that coat the exterior to make it easier for the phagocytic cells to move up. The alternative pathway, which was the other one we saw, basically factor B, factor D, and piperidin. C3b and B make C3 convertase. I'm not going to ask you to know this part. Okay, just the alternate pathway. Okay. And then C3 goes through its normal steps. The last one there is the MBL, or the mannose binding lectin pathway. This is just one more way that we can activate the complement, and this is another one for the alternate pathway in that we don't have to have the antigen antibody present. The classic pathway starts with that antigen antibody complex. The other pathway, the other methods, the alternative pathways including this mannose binding lectin pathway, the MBL pathway, basically are sort of more spontaneous. The sheer presence of mannose, which is not normally present in our cells, but is a major carbohydrate on bacteria, yeast, and some parasites. This mannose, which is just a sugar, okay, is a lectin that's going to bind to carbohydrate, or lectins are proteins that bind to carbohydrates. So the mannose is a sugar, which is a carbohydrate, right? Remember that sometimes. So this carbohydrate that is present sort of kickstarts the alternative pathway and leads down to the same thing.
Do they work together?
Yes.
I mean, both pathways would eventually be going at the same time?
Yes. Yes. Complement regulators, these are these inhibitors I told you about. They stop the complement cascade when it's no longer. If you let complement keep going, it's kind of like in the inflammatory, well, it is part of the inflammatory response. If we let that keep going without stopping it, what we wind up with is we wind up with tissue damage. Okay, and there's a lot of fairly new research that is showing that this constant inflammation and just sheer stress can lead to inflammatory reactions. So just being in a state of inflammatory, or just being in an inflammatory state can lead to all kinds of long-term and health risks. So the majority of the controls, since if you remember, what's our big chunk there in the middle from both pathways is C3. So most of our inhibitors, most of our controls are aimed at keeping that C3 molecule from being cleaved. Okay? They're keeping that C3 together. The number one that we see that we test for on any sort of regular basis, and it's not real common, is our C1q esterase inhibitor. This activates C1 in both the classical and in that mannose lectin pathway. We also have factor H, which is a regulator of the alternative pathway. But the biggest one that we really use is the C1 esterase. Disease states that we see here, deficiencies in C3 and C4 lead to bacterial infections, basically because the oxidization and the chemotaxis that are provided by the complement cascade get the neutrophils where they need to be and make sure they're eating what they're supposed to be eating. So without this complement cascade, you just gotta kind of hope that the neutrophils find them, sort of stumble on them by accident, okay, and eat them. Because even if they produce these antibodies and the complexes and go through the whole immune system, without this complement cascade, we don't proliferate that. We don't encourage the neutrophils to come in. We don't call to the rest of the body and say, I need more neutrophils. Okay? So they'll just sit there hanging out back in the circulating pools, and they won't ever go to the site of the infection. So you, like I said, the problem here is without this C3 and 4, without this complement cascade, we don't get our phagocytic cells coming to the site and doing what they're supposed to do. It's kind of a breakdown in communication. We see, especially important, we see complement problems when we have a gram-negative sepsis. And I know you guys haven't had microbiology yet, but we divide our bacteria into two basic categories based on a stain called the gram stain. How many of you have ever done that in a science class somewhere? Usually you've done something. The pink ones are negative and the purple ones are positive. And the structure of the cell membrane that causes that pink or purple color basically differentiates how these bacteria act in a lot of different circumstances. So gram-negative, especially gram-negative bacilli, are much more problematic. Well, sepsis is never good, but these gram-negative bacilli have a big problem that we will see an increased C3A and C5A. Our neutrophils come in and clump, and unfortunately it also kind of bumps into the coag cascade and increases our chances of thrombus. You can see pulmonary damage, pulmonary edema. They sort of build up in the lungs and give us problems. Myocardial infarction, which is a heart attack, increases levels of C3A and C5A that attach to the membranes and lead to more damage. They're in the heart muscle. So there's other chemicals and basically that can either start this complement cascade or inhibit its inhibition. Does that make sense? They can keep it from being regulated properly, which can lead to much more damage. Red blood cell lysis, cold autoimmune hemolytic anemias, especially when the red cells are warm to complement causes hemolysis. This is our basis for Donner-Landsteiner, for cold autoimmune hemolytic anemias. Okay, as long as they're cold, they're fine. As soon as you warm them up, they pop. This is not good. PCH, paroxysmal cold hemoglobinuria. When you're going into blood bank, see this all comes together, guys. When you're going into blood bank, when we start looking at our antibodies that we make against red cells, it's important to us to know, is it an IgG antibody or is it complement? And what we're going to look for when we're looking to see if it's a complement mediated antibody, we're going to look for C3 coating the cells. So when we do our DAT, when we're looking for antibodies on the surface of red cells, we're going to look to see, are they IgG or are they C3? So I said, this stuff all comes together in the end. Complement assays, we can measure quantitatively how much C3 and C4 you have. The most common, I think, is nephelometry, because it can give me a sort of quantitative measure of how much C3 and C4. One thing that you need to remember, and that's just because doctors never do, when doctors order a total complement, this is going to measure all of those complement components, all 30 proteins. He's looking for a CH50. So if a doctor orders a CH50, he wants to know how many total complement proteins you have. Normally, the CH50 is ordered in conjunction with the C3, C4. We kind of want all of those together. This basically is done by a hemolytic titration. We're going to make titers, we're going to make serial dilutions, just like you did the cold agglutinin. Only instead of looking for clumping, we're going to be looking for hemolysis. The titer is going to be the highest dilution where we still see hemolysis. Okay, does that make sense? Yes.
Did you say the CH50 is all 30? Is all 30?
Well, I don't know. It basically it's measuring the activity, not necessarily the quantitation of how much protein, but how well your complement is
So
working.
like a total complement is gonna be all, so you wouldn't see total complement in the C3 and the C4?
No,
because
you
it's
would.
in.
Hopefully you would see all of them together. That's going to give you
But I mean, wouldn't C3 and C4 be in a total complement?
yeah, C3 plus C4 would be portion
Okay.
of this total, but it would certainly not be all of it. And like I said here, the CH50 really is more of a titration assay to see how well your complement is working, how functional it is. Totally, utterly confused? through this one real quick. Do you guys have this one printed?
Yeah.
Does anyone need it still?
The
The next one.
cytokines, the one I printed.
Cytokines and immune response.
I printed
Um,
some that came
oh.
on the table.
There was a question asked earlier that I didn't answer. Tests. We had our first test today. The second test will be Friday. Okay. I have no idea what will be on it. We'll see what we get through. The second test will be Friday. The third test will be next Wednesday, because Jean's going to give you her last test on Monday and her final on Friday, right? So this is week 6, so yeah. And then our final test will be the last Monday. We'll have a quiz on Wednesday if we have to. I'm hoping not to have to. And then our final will be Friday. So basically, Monday, Friday, Wednesday, Monday, Friday. Okay? So there's gonna be 5 tests in here. And like I said, if we happen to fall behind and I need to give a quiz or an open book test of some sort for Wednesday, we might do that. I don't think we will. I usually get through this material pretty well. All right, part of this is actually going to be review. Okay, cytokines and the immune response. We've actually already talked about some of this. Some of these drawings will even be familiar. Okay. Definitions. Cell-mediated immunity. We've already talked about this. The T cells recognize antigens that are bound by the MHC class 1 and 2 proteins. They become activated and they produce lymphokines, most commonly interleukin. And actually, if you go back and watch the video that we watched the other day, he talks about where the interleukins come in. These are a chemical message produced by lymphocytes that influence the activities of other cells. They regulate the proliferation of T and B cells. We have to have some sort of communication between all of our cells. And basically that's what these cytokines are. This particular, and we talked about those a little bit in hematology, didn't we? Erythropoietin, thrombopoietin. Okay, some of the other ones that encourage our cells to differentiate and multiply the way they're supposed to. These protein messages, again, these are produced by cells other than the lymphocytes. And there's a number of cells that produce them. The adrenal cells in the kidney produce erythropoietin. The dendritic cells produce certain ones. They regulate the immune system, both the innate and the adaptive systems. Humoral immunity, this is where B cells receive a lymphokine message from the CD4 and are told to produce antibodies. These cytokines are how the CD4 and the CD8 cells regulate, tell the other lymphocytes what they're supposed to do. The innate system, or the passive or normal system we have hanging around. Interleukin 1 is produced by macrophages and monocytes to enhance the inflammatory condition. This is just one of the chemicals that causes an increase in the circulation to the site of injury or to the site of infection. The tumor necrosis factor, and I don't know what all the little @ signs. I think that's supposed to be a 2, and I think Gina can't type sometimes. So I'm pretty sure that's a 2, because if you look at the keyboard, the @ sign is what is on there. So this is tissue necrosis factor 2, or TNF2. It's also secreted by the macrophages and monocytes. Again, it simply increases vasodilation and vasopermeability. Okay? It swells our capillaries so that the membrane, the lining cells along them are kind of spread a little bit. So the white cells can come out, the plasma can ooze through more easily, and increase the proteins and the cells that we need to fight the infection. Interleukin 6 is produced both by lymphoid and non-lymphoid cells, and this is what stimulates the production of these acute phase reactant proteins and activates both the B and the T cells. The interferon is, and again, I'm assuming that's a 2. The interferons and the beta interferon produced by the dendritic cells. These basically produce proteins that interfere with viral replication. So the biggest thing that you need to remember here, interferon and viral go together. There's been a lot of different antiviral medications that rely on this interferon. Okay. The adaptive system cytokines, these are the specific immunity. These are related to specific immunity. They're mainly secreted by the T cells, so we generally call them lymphokines. We've got interleukins 2, 4, and 10 are the biggest ones. 2 is T cell growth factor. It makes T cells grow and differentiate. Okay. It also it also increases the lytic activity of the natural killer cells. It sort of turns them into super soldiers. The interleukin 4 basically is associated with helper T cells and helps to get a better immune antibody response. Okay, so interleukin 2 basically makes all of the lymphocytes reproduce, get bigger, get stronger, get faster. Okay, interleukin 4 pretty much helps CD4. So interleukin 4 and CD4 go together in promoting antibody response. And then interleukin 10, basically it has an inflammatory effect on a subset of the CD8 cells. Okay. And it inhibits the antigen presentation of macrophages and stimulates the CD8 cells. Basically, it says look at the cell, not at the antigens that are coming out. So 2, kind of everybody makes all of the T cells bigger, stronger, faster, or all of the lymphocytes bigger, stronger, faster. 4 helps CD4 make better antibody response, and 10 basically helps the macrophages encourage CD8 to eat up the infected cells. Colony stimulating factors, these are quite frankly a review. These cytokines are included as messengers. EPO is erythropoietin. Where is it produced? Kidneys. And it basically goes to the bone marrow and says, make more red cells. If you have somebody who has an infection and who has been ill, they're going to want to increase the amount of oxygen in their blood because oxygen is power, oxygen is strength, oxygen is energy. And you're going to need energy to your cells in order to fight off any kind of infection. The complement cascade, like any other biologic activity, requires energy to function. Our GM, all of our colony stimulating factors, basically goes through and G makes the granulocytes, M makes the macrophages, monocytes, and the granulocyte macrophage makes both of them. They act on bone marrow to stimulate the production of whatever cells we want. Okay, so if I've got some sort of bacterial infection, I'm going to see an increase in these granulocyte and granulocyte macrophage because granulocytes are primarily involved in fighting bacterial infection. That was like lecture 1 in hematology. All rolls back around. So as the immune system is stimulated, It stimulates not only these interleukins and the lymphokines, it also stimulates these CSFs, which are gonna go back to the bone marrow and say, hey, I need more white cells. I need more neutrophils. And the bone marrow is gonna go, okay, and it's going to make them. Which is why, and neutrophils mature very rapidly. So within just a very short period of time, the first thing that happens, one of the cytokines goes out and says, release the extra ones that you've got sitting in the marginating pools. Because you have neutrophils, which are just sort of hanging around in your body doing nothing until they're called to action. So one of the first cytokines that comes out brings those out of storage and puts them into circulation. As those are pulled from the storage pools release, the cells around the storage pools release these stimulating factors and go to the bone marrow and say, hey, I'm empty, I need to order some more. When the activity ceases, when the leukocytes are no longer needed, the whole feedback loop falls apart, things start to build up in the storage pools. We don't need these, so the storage pools don't produce a call for more, and everything kind of goes back to normal. It's amazing where you're alive, isn't it? Okay, T-cell activation. Again, a lot of this is actually review. This is stuff we've talked about in other pieces, just not in the same order, okay? T-cell activation occurs most commonly in the spleen and in the lymph nodes, where the T cells come in contact with the antigens from the macrophage. Okay? Just like we talked about before. Yes?
I thought you said T cells were activated in the thyroid, or the thymus, and the B cells were activated in the thymus.
No, they mature
Mature now.
in the thymus.
So there's a difference
They
between
then
activation and
move.
mature.
They then move to the spleen and the lymph nodes where they become active. Okay. So in the spleen and in the lymph nodes, the macrophages have lunch, present the antigens to the T cells. What does this? How does the macrophage present the antigens to the T cells? How does the macrophage present the antigens to the T cells?
As the antigen antibody complex does.
Nope. How does the macrophage present? What is this right here? What is that little piece?
Throw up. Cell throw up.
You're getting there. I'm not giving you the answer. We'll be here all day to figure it out. What have we already talked about? How does the macrophage? What's that?
Isn't it this little piece out there, the stuff in it?
Right, and what do we call that?
Complex.
The MHC, the Major Histocompatibility Complex, Class 2. We talked about this again. See, it's all coming back. It's coming back to haunt us. No, we just took the test. We don't have to remember anymore. Okay? The macrophages take the antigens from what they ate, pop it onto that MHC complex, which then presents it to the T cells. Where's our music? Where the sounds of the noise? Okay. The CD4 cells recognize the MHC class 2 antigens on the surface of the macrophage. The macrophage is also known as an antigen presenting cell. Why? Because it presents antigens. Very complicated naming mechanism here. The macrophages produce interleukin 1, which is a cytokine that stimulates the CD4 cells to produce interleukin 2. which then does what? 2 slides ago. What does interleukin 2 do? What? What does interleukin 2 do? Grow. Interleukin 2 makes all of our lymphocytes bigger, stronger, faster, and more of them. Okay? It tells lymphocytes, make more. It says multiply. Clone yourselves. Okay? Because remember, mature lymphocytes are the only leukocyte which in its mature form can make more. And it does that not by making babies and mitosis, but by, but by cloning. Okay? It doesn't make more blasts and go through maturation sequence. It clones itself. It clones mature cells. So this interleukin 2 stimulates cloning so that here's my macrophage. Here's my MHC complex 2, which is presenting antigens to my CD4 cell. Okay? The macrophage secretes interleukin 1, which tells the CD4 cell, hey, it's here, take it. Is there another class that comes in
I
here?
think so. I think Monday and Tuesday there might be.
Oh, let me make sure. Sorry. Okay, we'll pick this up in the other. CD4 is to produce interleukin 2, which tells the T cells you need more T cells, go clone your cells, get bigger, get stronger, get faster. And that makes a rapid multiplication of more CD4 cells. So these helper cells, these CD4 helper cells, are now cloning themselves. And each one of these CD4 helper cells is going to run around to the other B cells and say, make these antibodies. Okay? So it's sending out its little messengers out and saying, go make all these antibodies. Some of the cells that it tells to make antibodies are going to be sequestered back as memory cells. Okay? These memory cells are what are going to hang around so that if this guy shows back up again, you're going to have a much more rapid, much stronger second response to that disease state.
Did you say the helper T cells were the only cells that could clone themselves like that?
No, just lymphocytes are the only cells that can clone. Yeah, your granulocytes, your monocytes, they do not clone themselves. The only ones that clone are the lymphocytes. T cell activation, and these are the CD8 cells. These do the same thing as the target cells. So instead of having a macrophage that's sort of, giving leftovers to the helper cell saying these are the bad things, this cell, if you remember right, our MHC1 class, or MHC class 1 system shows the body infected or tumor or abnormal cells. Okay? So what's going to happen here, these CD8, which are the cytotoxic or the suppressor cells, are going to recognize the fact that the normal antigens that are on the MHC1 complex are not there. The little "it's me" sign is missing. And in its place is a "this is not me" sign. Okay? So the cells basically sacrifice themselves and say, hey, bad guys are here. You need to come get rid of them. Okay? The CD8 cells produce lymphotoxins that destroy the target cell. Okay? And also interferons that interfere with viral replication. Because what happens, unfortunately, is when you burst this cell, all those little viral particles are released. And where are they going to go?
Other cells?
other cells, and they're going to infect a bunch of other cells. So what this CD8 cell does is it makes a lymphotoxin and kills off the bad cell. Bless you. But it also secretes interferon, which is one of these cytokines, that prevents the virus from replicating and infecting more cells.
Is that kind of like what zinc does for the common cold?
I have no idea what
Okay.
zinc does.
Never mind.
That one's, I haven't, it's on my list of things. I don't know if it actually does anything or not. So, if it helps and it's psychosomatic, don't tell people and it'll keep helping.
Is it essentially just attaching to those little things and saying, hey, attach to me, not this other cell?
I have no idea.
Just, okay.
I really don't know. My B cell activation, okay, lymphokine 2, IL-2, interleukin 2, causes B cells to proliferate and differentiate into plasma cells. We just talked about this. Those CD4 cells are going to go out there and they're going to say, hey, you need to grow up, you need to make antibodies, and you need to start spitting those out. So the plasma cells will start creating, or the B cells will turn into plasma cells, which will start issuing forth antibodies. Plasma cells ultimately produce antibodies, and some of those plasma cells kind of hang around as memory cells. Okay?
If it's a memory cell, it's not going to produce an antibody, correct?
It doesn't until
It's activated?
it's activated again. Yep. And obviously, the closer to the initial infection that you get, the stronger that secondary exposure is going to be. If it's been a long time since you were exposed to it, well, then you may not have quite as many memory cells still hanging around. You may not have quite as good a secondary response, which is why every few years you need your Tdap and you need your tetanus booster, or why you need boosters on some of the different vaccines that we have out there. Let's just throw this out here for fun, see if we can figure it out. I've had colds. I've had colds tons of times. How come I still keep getting new colds?
Different strains?
It's a different strain. It's a different rhinovirus. So each one is its own thing. It doesn't take much to change the virus into a different one. So yeah, I've had a cold. That's why we can't cure the common cold. Okay. We just haven't.
Get
And
ahead of it?
honestly, do we want to cure the common cold? Okay, I mean, yeah, that's miserable. It doesn't feel good. They want to sip about study doses. But truthfully, it's not fatal to most, and it does keep our immune system going. We don't want our immune system to get lazy now, do we?
Isn't there a chance of it eventually developing into a strain that our bodies can't fight off, though?
Oh yeah, always. Superbugs are gonna come someday and wipe us all out. I don't know when that's gonna be. We've been here for what, 250,000 years? Let's see how much longer we're here. You know, as far as evolution's concerned, 250,000 years is a blink of an eye. So, we'll see how much longer we stick around. B cell activation. We've already talked about this. I drew the picture on the board. We have our first exposure. There's always what we call a lag phase, okay? And that lag phase is kind of, oh, here's an antigen. Okay, oh gosh, okay, we're gonna put this out here in the B cells, okay? They're gonna go make the plasma cells. It's gonna take us a few minutes to kind of get that production line in gear. It's gonna take us a little bit to start because we're starting from scratch. We have to make new templates, we have to grow new cells, we have to clone them. We got a lot of stuff we gotta do to get that going, okay? Once we get started, we're gonna get some of those B cells, they're gonna start secreting that immunoglobulin M, that IgM, that first responder. Our acute phase antibody, there's 5 pieces on this guy, so it can go out there and glom onto a lot of it, okay? Before the IgM even reaches its peak, we start making our IgG, okay? The secondary response, the second time or subsequent times that we're exposed, that lag phase is much shorter. Why? Well, we already got all the mechanisms in place. We just got to turn it back on. Okay? We already have the template. We don't have to make a new template. We don't have to wait for those B cells to figure out what the antibody should look like. They already know. Those memory cells are there. They say, look, hey, we've seen this guy before. It looks like this. Make more of these ones, okay? And the body automatically starts churning those out. So that response is much, much faster. My IgM response is, if not immediate, very, very quick. It doesn't get quite as strong an IgM response, basically, because the IgG kicks in there and says, I got this, guys. We're good. I don't need as many of those difficult ones to make. You know, you got to put all 5 of these things together to make an IgM. You can just spit out the monomers, and you can spit out a bazillion of them real fast. And that's what's going to make a better second response. That IgG titer is going to remain elevated for quite some time. Okay? Just to make sure it's got all of them. Eventually, it will drop back down. And it depends on the disease state, how long it will take it to drop back down. In some cases it may be a couple of days, and in some cases it may be a couple of years before that titer really starts to drop back. I told you that was all stuff we talked about before. It was just more come at it from a different angle. Questions, problems, complaints. Those 2 will definitely be on Friday's test. For sure. All right.